Okay, hello everyone. I guess we can start. Everybody more or less here. So today we will discuss another approach of making ensembles of basic models called boosting. So we develop the training algorithm and compare to the other approach, namely bagging. Okay, let's start. So you can ask questions by voice. Don't hesitate to interrupt me. In any moment, you can ask a question on English, on Russian, whatever you like. And also you could write them on chat. I will try to keep an eye on chat also. Okay, let's start. So let's recap what we have with bagging. What properties of ensemble. So this will be ensemble of n base models, and so then this guy is a notation for base model. So then we know that in bagging, bias of the whole ensemble will be the same as the member. Yeah, for n. Yeah, but however, we know that the variance of the whole ensemble could be decomposed as this average variance of each model plus covariance between ensemble members. So then, if this term is 0 or nearly 0, then the variance is decreasing. So, and the much as like this, the more models we have, but given that covariance is not increasing, then better results in terms of variance decreasing we obtain. Yeah, however, like crucial drawback maybe here is that the bias is fixed. So then we could, the whole idea and the whole point to trying to develop other approach of ensembling models than just averaging them when they train independently is to somehow mitigate the bias. So we would like not to decrease the variance, but we more worried about bias of basic model. Yeah, and as usual example of bagging is trees. So here we have some picture for two-dimensional. So we have one feature and one-dimensional target here. Yeah, and we see that in the presence of some outliers, I will just highlight them. Yeah, some of the trees are starting to be very picky around them. So, and this is a characterization of the high variance. Yeah, on the opposite side, if we train bag trees, we see now then different models of bagging trees, of course, also somehow influenced by outliers, but a lot of less. So we have a lot stable line here. And this is a like just graphical illustration of previous statements. Okay, so then let's formalize what the problems or drawbacks of the bagging. So what is our motivation? So let's assume that Bn is highly biased. Yeah, and then the whole ensemble An, which is just average of these guys, has same bias. Yeah, and this somehow restricts us and saying that like the performance of ensemble in terms of bias will be the same as well as we could do with one model. And somehow it's maybe not satisfying because we would like to have a way of how to take small bricks of our models and increase the whole expressibility of ensemble. Other drawback is like computational time, maybe not drawback. But what is like original motivation was with this? Yeah, that is good for large N. So in beginning, what was? We train all models independently. And then we can train them in parallel in time. So for basically, for any N, we can add just more resource, computational power, and so we will have same result in same amount of time. Yeah, and now if you're talking about that, we would like to reduce the bias of the ensemble, then we cannot do this independently. So we need to do this sequentially. And that means that it will be some price that we pay for that. So we, let's say that price in terms of time. We will need to spend much more time with this. Yeah, but still, what does it mean for us? It means that we should not train for a lot, like very large N. We should take some reasonable N. And we have hope that some reasonable N would be enough, because now we would train sequentially each model. And so we could affect more effectively on the performance of ensemble with each new model. Yeah, and this is like the whole idea of boosting. So what we make in boosting, we will take very simple models. As base learners. Yeah. And why we can watch, I mean by saying simple, that they could have high bias. Yeah, and this is quite opposite for backend case when we need to take low bias basic model. So this means that it's somehow a complicated model. Yes, example. So here we should take very depth trees, like with depth around 8. And here we should take not so depth trees, like with depth around 3 or 2, something like this. Let's also note that high bias, but low variance. Because with if we train sequentially by adapting to previous models, then we of course will have high variance. So then each model should have low variance to overall variance not be so high. And this is again opposite to the backend case, because we should use low bias model, but we are not really restricted on variance. Because we know that when we do this independently and then averaging, then we will decrease variance and we will be fine. Okay, then here's sequential training. And here again, as opposite, so independent, and that's mean training in parallel. Yeah, we could also provide some intuition for now what does it mean sequentially. So we would like to new model. Let's say new model B and corrects the whole ensemble I, A, N -1. Yeah, and this is somehow sequentially. Okay. So we have a plan. At least we know the properties which we would like to reach with boosting. So now we need to develop a training procedure, how to do this. So let's do this. So this is our ensemble. Each of BN is a base model. And so we would like to sequentially learn all n of them. So for the first model, it's very easy. We already know what to do. So we have some loss function, which is depend only for our task. So it's fixed for training the all members of ensemble. Also, we have some fixed training data sets. So it's our training data. And we choose some class of models for the first member, one. So then we need to somehow minimize it over this. And this is easy. This is like usual problem that we already solved for any model. For regression, you will optimize over coefficients. For trees, you will make greedy learning over the splits, and so on. Whoa. Okay. So what about next models? Let's say that we learned already B1 and all till Bn minus 1. So they are fixed. And that means that we not really care about them. So then we could write the optimization problem for Bn member. And let's also see that this part, the previous part of ensemble, is fixed. And this we need to learn. But now it's become a bit more problematic. Because, okay, maybe if this guy, so we have two variants. Yeah, so this guy could depend over some parameters in a smooth way. Then it's okay. Yeah, we could just perform gradient optimization and that's it. But usually we are more interested in some not so smooth models, and like most useful example are trees. So if Bn is 3, what to do? How to optimize this optimization problem? Because again, we know how to optimize it to solve this problem. And you see the difference. Here you have your model and the target. And here you have your model, your target, and something else. Yeah, some previous result of learning other members of ensemble. So we should somehow modify the training procedure for BN. Okay. So how we can do this? And what criteria of modification of procedure? So we don't know how to optimize this. We need to introduce some algorithm. And of course, we can do this model specific way. Yeah, so if you're saying for me BN is this kind of models, then we could analyze this particular these models and develop some algorithm. Also, it will depend maybe for loss function. Yeah, but we would like to provide some very general algorithm. So with modification should work for any loss function and any models BN. Yeah, and this like quite restrictive assumption on what modification we can do, because it's saying for us that like what we would like to reach if this, we would like to, if Bn, let's assume some model from a scalar, and it had the method fit. So we would like to only modify this part, and all routine inside of fit keep the same. Yeah, then you give me any model of Bn, any loss function, I press the fit and only modify what I put here in this part. And so let's make some steps to reach this. And the first case, which will be easier and will provide for us intuition how to do this, it's okay. Let's take the simplest loss. Let's take the MSE loss. Can we do something with this? So again, we have our optimization problem. We write it, and we consider MSE loss. So in an MSE loss, usually this one is what? Is a data point that we observe. And this is prediction from the model. Okay, and in our case here, the prediction of the model is this whole, like the red is the red. So we take the old part of ensemble here. We could write it maybe. Yeah, and then this is plus new model. Okay, but you see, like this loss is very simple. It has an additive structure, so we could rewrite we could plug in and then rewrite in the following way. Yeah, and then what happens? So this is our new model. And this is modified target. Yeah, and this was possible just because MSE loss is a square of difference of any two numbers. And so I could put bracket whatever I like. So there is not much difference here. But in terms of like, how we will train the new algorithm, is much different because now we know that this is just our new target and that's it. Yeah, and then we could a bit formalize it and say that we could call this guy residuals. And then this problem of trading ends model, we could say that this is a problem of matching the residuals. Or errors of ensemble. Okay. Also, we could imagine that, so let's assume that on some object, this guy is equal to 0. Yeah, what does it mean? Then it means that we already predict on that object perfectly, and there is no need to modify anything on this object. So then we say for while training our new model Bn that it should output 0 on this object. And like this is desirable behavior because we know we don't make any mistakes on this object already. So let's not introduce anything off top, just output 0. So if SI is not 0, then it's equal to something, and this is exactly what we need to add to the output of our ensemble to reduce the error to 0. Yep. So okay, we could also have a simple example. So if this guy is 12, this guy is 10, so residual will be 2. This will be plus 2. And overall output should be 12. Yeah. And this is all like so easy because we know MSE laws has very simple additive structure. But this gives for us at least what we desire. We could now take any model BN and just use its fit method just by introducing another targets, and that's it. So first iteration is okay. Second iteration, we say we modify targets and solve a usual optimization problem, usual fit problem of our algorithm, also okay, and so on. So for the third target, we will take the difference between what we observe in training data set with difference that we learned as member of our ensemble. So it's also fine. So we now know how to solve the problems for regression at least. Yeah, let's take an example. So this is our feature. This is target. So let's see how it will be works. So here we fit a very simple model. You can see that it's a very simple model because you exactly 3 regions here. So it's 3 with a number of the depths of 2. So what we do here, we take any point here, like there, measure the difference between our prediction and point and what we obtain. So this is zero level. Yeah, let me draw it more accurately. Yeah, and as for this bunch of points, we not make any mistakes really, make some small mistakes. So then residuals is around 0 here. Here we make some big positive mistakes. So these points above the line, residuals is highly positive. For this, we make negative mistakes. So we have for this bunch of point negative residuals and so on. Again, positive and again, negative for this and these guys. So then we train second model in such way that here output 0, here output slightly positive, here slightly negative, and so on. And that's it. Yeah, because we have restricted class of capacity for new model, it also cannot fit like for this whole task, but it could fit for some of them, partially at least. It's select OK. I will modify only this part, yeah, because it's this I can do. And so this is modification of our procedure. And again, we have residuals, so still 0 here, as we not introduced new mistakes. Here we nearly like done a bit better, so this is decreasing level of residual. Here as we fit great, so this now in the 0 line, and so on. You can see this step by step, this all residuals getting near the 0. Okay, so let's then answer the question, will we overfit or not? And maybe provide some intuition why so. So here is the random forest picture. So it's basically it's a bagging. Yeah, for bagging, like we know the general decomposition of the error. It's squared bias plus variance plus noise, of course. And this is like whole error. Yeah, and we see like random forest with different amounts of features. And before some period, its error is decreasing with the increasing number of estimators. And then it's like become to fluctuating and nearly it's on the same line. Yeah, like what is the gap between these guys? It is because it's have different number of features. But also it has as number of estimates is growing, it's harder and harder to get estimators that are not positively correlated with each other. So we have this term starting to a bit, maybe not really great increasing, but some of them like decrease overall, but then some small amount of a bit increasing. You should understand that like the covariance is also increasing in this term proportionally to this guy. Yeah, so if you already have more than 100 estimators, the new one correlated will a bit increase it. And so it starts to fluctuate here. But overall, it will never increase lower because also, so this is a bias of the model and we cannot increase this. So it will, I would say, with number of estimators growing much more, you will have like very the same behavior, like something like this here, and like this here, and like this here. Yeah, well, then let's see same picture for boosting. Yeah, what we have. We have that on train. We could decrease rapidly with, so this is a number of estimators. And if we a bit extend, we can get perfectly to 0 here. And here we will start a bit increasing. Yeah. So the first point is that boosting is overfitting. And I get the intuition, the intuition of this is clearly from like our example with regression on one-dimensional data. We fit on our own error on training data set. So what we do, we really somehow overfitting. Yeah, but the nice point of this is that it's overfitting slowly. Yeah. So why slowly? Because we're saying that we would like to use simple models as base learning. So they have low variance and big bias. Yeah, and then somehow when we summing up them all, we reduce loss much further than we overtrain. And this is of course like a bit hand wavy, and you should empirically you always will observe some trade-offs because this word slower or big relative to your data set, to your model, to hyperparameters of base learners. Yeah, for example, for some data sets, taking the tree with depths, like 5 will be also a low variance model. But for some, it will be completely overfit very fast. And also we'll later discuss like hyperparameters as step size, but basically it's just this which you add a new model here. And if you get this guy, provide for it very high value, of course, variance will be increased and you will overfit much faster. Yeah, but what is takeaway message from here? That from beginning you have no problems with overfitting. You will never overfit, but you will just reach some non-decreasing error, which you can obtain on training or on the test data set, and you can do with it nothing. With boosting, all is quite opposite. You can overfit, but this is the price for that. You can decrease the error on your test data set much further than with bagging, because you could make BS lower. Okay, let's go further. Yeah, so this like simple outlines that we know how to deal with seamless kilos. We know that we can overfit. So then we should go somehow beyond MSE. And we would like to keep the same procedures, that we only modify the target and use like basic fit methods for any models that we would like to use as base learner. So what does it mean beyond? Well, like the first maybe example that we would like to have is to solve classification problems. And this means that we need to deal with log loss. But also we could imagine some other problems. For example, we could have quantile regression. Yeah, basically when we put some asymmetric loss, something like this. Yeah, so let's call this F. Okay, so somehow we need to modify then our procedure, because we will see an example where it's like our current approach doesn't work, but in general it's clear. Yeah, so MSE loss has very simple additive structure. So here inside you can put brackets whatever you want, and log loss or any other non-linear log, not non-linear, not so simple inside, will have some problems. Okay, but let's see. So recap again, we have our ensemble. We would like to train ends model, and we would like to keep this guy fixed. So we need to solve this problem. And what we did before for MSE loss, we just saying, okay, instead of this optimization problem, we will use this optimization problem. Yeah, so from, let me emphasize the difference. That this guy was here, and now we have here. Yeah, and for MSE, it was a valid thing to do because we just put bracket in different places, and that's it. But what we will obtain if we do this for different algorithm? Okay, let's consider logistic regression. So we define this guy as residual. Yeah, and then put this our target. So this is output of our new algorithm. And so this is our loss. And this is our rule of for output. Yeah, because we in classification we assume that our target labels are -1, 1. Yeah, then we could say what will be residuals here. So what it could be? This could be +1, and this will be +1. So it will be 0. This will be -1, and this could be -1, so it also would be 0. And it could be plus minus 1 and minus plus 1 here. So it will be plus minus 2. Yeah, this is like already a bit confusing because so this will be our new target here. Yeah, it will be 0 and plus minus 2. And our algorithm should output something which is valued minus 1 and 1. But okay, we could say that any base algorithm output anything, which is already a bit restrictive because usually what we do, we train base models on something for classification that's already suitable for classification. So they itself output something like minus 1 and 1. But okay, we could take these models like anything and then modify and ensemble in this way. Yeah, but let's then see what how this training points here will affect on the performance of this algorithm. What will it learn? Okay. So if you take this guy, so if O residual is equal to 0, so this means that we already predict correctly with this the current ensemble. We already predict correct label for object xi. So we have this be equal to 0. So we just, what does it say? We just don't use this point in our training. Yeah, and in first it could be viewed as okay. So if you're already not making any mistake on this object, let's train our new member of ensemble on the other points. But this will lead that when we will predict this new algorithm on this point, which we already classified correctly, it could output anything here. And this is quite like serious problem because like with minus plus minus 2 we can deal. We can just like multiply here by 1/2. Yeah, a bit modify the loss, but not very hardly. And labels again will be plus and minus 1. Yeah, but when we modify the output of the whole ensemble on the objects that we already classify correctly, that's a problem, because now we can not guarantee that we will improve our performance with each new member of the ensemble. That's showing that our modification, like the simple using same modification of training procedure as for MSE loss, not working. We need to somehow do some other steps to get performance. Okay. Okay, and so let's think about what we can do. So what we have, we know that for MSE we are fine. Yeah. But we know also that for some other functions, like log loss, we are not fine. But usually as a loss function, what we use somehow convex functions. Yeah. And what does it mean to function to be convex? It means that function is convex when locally, at least, it could be well approximated with parabola. Yeah, but this means that any loss function in a point could be very well approximated with something which is behaves similarly with which is log low. Similarly with MSE loss. Yeah. Then the whole procedure is look very similar as gradient descent. Yeah, so this is our current algorithm, so current ensemble. And we somehow linearize the problem around this point. Yeah. Physically, like practically, we just approximate the loss function around current ensemble to be more like MSE. Yeah, and then just we would like to make step on this direction. So in the gradient descent, we just make step along the gradient of function, which we optimize. Yeah, so this will lead to optimization of this. Yeah, here we would like to make, say that the new ensemble is a old ensemble plus a new member. And this new member should be trained on the gradient of the loss function. Yeah, and this will lead this problem be similar as the training to MSE, and always will work. Yep. So what we have? We have the following optimization problem, and we define the residual for each object. So let me, this is important. This is defined for each object. Be equal to the gradient of the loss function. In which point? In point of the answers of the old part of algorithm. Yeah, so we linearize our problem like 2 times. The first time where we linearize it in the space of our functions, of our algorithms. We say we will modify this guy varies like a bit. Yeah, we will just add something here. And then we go in like inside our loss function and linearize it one more time. We're saying that what modification we need to do for this, like some highly complicated, maybe as log loss function, like the same as a linear response to it. Yeah, let's match the gradient of this loss function. Yeah, and what is all linked these steps is the point in which we take the gradient of the loss function. The point is answers of old algorithm. So here it is there. Yeah, and we could like maybe also say that, okay, for each, it simply means that for each member of the sum, we say, okay, we could approximate it with something like this. Yeah, multiply by the difference here and like something beyond. Yeah, but here what we're trying to do, we say that, okay, this could be like approximated with that just first order expansion as a current performance plus modification. And then let's mimic this, and this new algorithm should match this modification here. Yeah, and we would like to reduce the loss, so it should match it's negatively. So it's come minus sign here. Okay. Okay, so this is just, we take the derivative. This is our answers from training set. This is ensemble output. Yeah, maybe what's important here to say that this is not about parameters. and we take the derivative with respect to answers of the ensemble output, which this guy is fixed. Yeah, we don't take the derivative with respect to parameters of this guy. Or not what we do. Okay, so then this will be all okay, because if we what is possibilities? So if predict correctly, what does it mean? Then will be equal to 0. And usually what loss function we use that the 0 is the minimal point. So then the gradient will be also equal to 0. And this whole will be equal to 0. And new algorithm then will be saying that, okay, in this object, you should output the 0. So not modify the whole answers. And like, also it could be negative or positive error. And this will be like saying to making like its loss less or greater. Or if we are talking about log loss, so it will depend on the sign of the gradient. And this will provide you like useful signal to the learning of the new model. Yeah, so what is also important that the residual is some real number. And so then our model should output so we feed base model on it. Yeah, but how we could feed some model on some real output? Yeah, is this just regression task? And so then we all boil down to optimization of MSE loss. Yeah, so this is our new model. This is this residuals. And what we do, we just solve the regression problem. And this is nice because now whatever loss function we have as a target loss function in our overall problem, we break this to the solving several regression tasks. Yeah, and for regression, we could like do like just this. Of course, you could also modify this inside problems and take saying that, okay, I would like to solve this regression problem not with optimizing squared loss, but absolute value or whatever. You could like in private. Theoretically, you can do this, but in practice, there will be no difference because these models have, like, let's say, they're simple models. Yeah, so they will not overfit to these residuals. Okay. So let's like recap what I said. So we fit new model, maybe except the first one, with solving regression problems. We define these guys to be and call them residuals. Yeah, again, this is derivative of loss function in each training point, but derivative over the outputs of the already learned algorithm. So and because of this, it could be viewed as a gradient descent. In space of the like informally space of possible answers. Yeah, in space of what our model could output as an answer. But more formally, it's in some functional space. Yeah, because like each model that we fit this is actually some function which we constrain only on the data points, and on all other points it behaves how it's like. Also important point that with this we use local information about our loss. Yeah, and this is somehow missed maybe point in our discussion, but maybe we discussed it when we talk about GLM models. So from this, it be clear that loss functions that we use to optimize, to solve any task, they should be convex, and also they should be strictly convex. Yes, they should have unique minimum value. Yeah, because otherwise we will have problems here. So it will be not clear why we need to match this, why, and also residual could have non-zero value in the optimal place and so on. So this is our requirement to the loss functions that we use, but it's not really restrictive because other loss function not interested for us. Yeah, and final point maybe that you can, so maybe logic a bit complicated of derivation of the whole algorithm, but for MSE loss it was very simple. Yeah, so I guess for MSE loss you can easily recap it by yourself. Just if I write you a problem and ask to do this for MSE loss, you will eventually come to the same algorithm. So for MSE is fine, and then that idea is that you need maybe to keep in mind just that any loss locally is MSE loss. Yeah, and locally it means around the current answer of ensemble, and that's it. So what we do, we say, okay, we have some model, it outputs some numbers. Locally, each number provides for us some error, which is similar to MSE loss. Then we fit next model just on these errors around each data point. Yeah, and to do this, to say locally more precise, we're saying that, okay, our target is the gradient of the loss in that data point in the answer or with respect to answers of previous algorithm. Yeah, okay, so let's check that at least what we done is the same, will be the same for MSE loss, because otherwise it will be strange if we obtain some different results with this approach. And okay, what we need to do, we say, okay, residuals is the stuff, so the gradient of the loss function with respect to the answers of previous ensemble members. So we just write the definition of the MSE loss, take this gradient to here, go here, so we obtain this one guy, apply minus, okay. We recap the same procedure that we have like heuristically derived from MSE loss. Yeah, then the indeed problem is the same. We need to fit to this residuals, and this is the same result. Okay, let's also say take a look for some other losses. For example, we would like to punish for mistake which is higher than the target, more than for mistake that's lower than the target. Yeah, like 5 times. So then we make what we need to make. We take the gradients with respect to that. So in the point of the answer previous algorithm, and of course we will have like here is going to be just linear terms. This 2 is going to this 1/2. Yeah, and indicator functions keep here. So we will need to fit to these residuals, and if that, so if in some particular points the answer of ensemble is higher than target value, then we feed to this part. If it's lower, then we feed to this part. Yeah, and the same stuff for any loss function. So this is also an advantage, and all boosting libraries allow you to use your loss functions. Only that you need to keep in mind that your loss function should be some convex function. So it could be convex function itself, or it could be a linear combination, just sum, like here, sum of convex function, and so on. But you need to adjust. So basically, you need to define a loss, which takes like prediction and true value, and also you need to define what? You need to define what is gradient. So we also need to define function like grad loss, which is again true value and point where to estimate, and then just program it here, and all will work. Okay, this is just example with numbers, but it's pretty easy. What is maybe more interesting is logistic function. So let's go through it. Okay, again, we define what we need to do. Then we just write the loss function, take the derivative, and obtain the following value as our target. Yeah, so on that we need to fit to this. Yeah. So let's take a look that here we will have in nominator -1 or 1. And here what can we have? So this is -1 or 1. Yeah. This is also -1 to 1. So let's see. So if we are correct, so this means that this product will be much greater than 0. Yeah, so firstly it will be positive because we make correct prediction. So the sign of this guy and this guy should be the same. And like why it's greater than 0, because you can recall this all the stuff of discussion about margin and confidence of algorithm. So if we have like several algorithms that making correct prediction of this, it probably would be highly positive. Okay, or maybe if it's not highly positive, it will be okay. At least it will be positive. So then we take to the exponent some positive number and divide over all. Yeah, then it will be something around than 0, because we take some finite number like -1 or 1 and divide it for something that is exponential of positive number. So it's clearly become this is large, this is small. We get something around 0. On the other side, if we output something mistake we make, so we have this number to be negative, because like to make mistake is means that we output the other sign, then it should be on our training value. So then again, what we have, this is fixed -1 1. This is 1 plus exponential of something some negative number. So this guy will go into the 0. Yeah, and we will obtain something y divided by something nearly that 1. So we nearly output have +1 or -1. Yeah, so this is good properties, because when we feed a new algorithm to our residuals for classification problem with log loss, what does it mean that we have that? If we're already making some confident correct prediction, we will say that, okay, new algorithm on this object should be output 0, not to modify previous answers. Yeah, and if you make mistakes, we just provide to algorithm to feed something like the label -1 or 1, and this is also nice property. Okay, so then we correct. So we obtain desirable result, which is quite opposite to that case that when we are trying to somehow just heuristically change our optimization problem with log loss. Okay, so finally, what we need to discuss is hyperparameters. And maybe important hyperparameter is learning rate. Yeah. Or we could call it step size. So usual heuristic is take the step size on this number between 0 and 1. And this is somehow like the whole general intuition is something like similar to learning rate in just usual optimization and gradient descent. Yeah, not like exactly the same, but if you have some questions, you can think about gradient descent first and then saying, okay, it should behave something like this. Yeah. So we are only interested in this part. Fine. Yeah, because it's like, if you would like to take some big value of step size, then it's at least a bit the same as rescaling the output of the whole algorithm. But if you first feed the algorithm and only next apply the fixed step size, it will affect one time later. So it's better to make small step sizes. So because of this, we concentrate our attention here. And what is like usual observations maybe. So if you take like smaller step size, you will need a bigger number of ensemble members. Yeah, and this means that for each adding member, you will have still bigger bias, but you keep low variance. Yeah, because if you have something already much members here, and you only modify your output a bit, so you decrease your bias and like proportionally to your step size, because you multiply all outputs on this number. Yeah, but you keep your like the whole structure low variance, and like this is always trade-off that you can change. So for example, you can have like more tree with more depths here as base learners, but multiply them on the small step size. Or you can have like, with depths 2 take trees but multiply for step size 1. And for each task, you need to somehow just see how to the performance of your procedure, like for example, cross-validation, or just make small portion of data and observe. Yeah, because it's hard to say something very general for any data set, for any base learner. General recommendation is just saying, okay, this algorithm is really sensitive to the step size. So you need to choose it. And also you could keep in mind that if you take some expressive model as base learners, then probably you will need a lower step size. If you take some very restrictive model-based learners, then probably you can take the big step size. Also, if you take really small step size, then you should keep in mind that, okay, I need to increase the number of models in my ensemble. If you take the big step size that you say, okay, then maybe not so much members I need to have an ensemble. And basically, that's it. Okay, let's take a look on some particular example. So what we have here, we have error on the test. We have total number of trees on the whole ensemble, and we have for each curve we have different learning rate. Yeah, so let's see. Okay, so like this yellow line has the fastest decrease of the error, but then it starts to increase. Yeah, and not surprisingly, it has the biggest learning rate. So with a few models, they're very influential on the output of the ensemble because the weight of each model is 1. So it's really fast decreasing the error, but then it's starting to a bit overfit, and then it's starting to, like, if still you have some restricted model, then you cannot fit perfectly on each error, and you go in the cycle because each model affect very highly, because learning rate is equal to 1 to the output of the whole ensemble, and you start to this correct it, but make new errors, and new model corrects that errors, but make new errors, and so on. Yeah, and then like same stuff for this aquamarine line. Yeah, and the most lower decreasing is with the smallest learning rate. Yeah. So maybe some, like, the answer is on the gray line, so it have in somehow in the middle size learning rate. So it's decreasing very smoothly with enriching number of trees. Yeah, but also it's like depends how maybe what is better for each example, because maybe it's better to take like smaller numbers of trees that will be fine with this number of trees, and it's okay. Then you need, of course, a higher step size. Also, common hyperparameter is to send to be trees to be somehow restrictive and not to overfit, and this leads us to regularization of this problem. And like as always for regularization, anything that keep in your mind is work. So like any kind of randomization, yeah, so we can restrict number of features for each base learner. Also, we can restrict number of data points. So we use subsample. Yeah, and this is like the same rules of this as for bagging. Yeah, but I would like to emphasize that for different reasons. So for bagging, we do this because we would like our tree to be different. Yeah, and to have less covariance. Here, we would like, if we would like to use somehow maybe less members of ensemble overall, so we would like to use more deeper trees, but then still we need to constrain each base member of ensemble to have low variance. And to do this, we say, okay, we will provide small number of features or small subsample of data points and something like this. Also, like because we mostly talking about trees when we're talking about ensembling something. all kind of pruning. It's also fine, or maybe some like restrictive members of trees, some like extremely oblivious trees, or some like, I don't remember the name, but which are sharing the feature, cross splits. Yeah, also you could add noise to the target for each tree. Yeah, just generate some normal noise and add to it. It also helps to avoid overfitting. Okay. So that's the whole that I would like to tell you about boosting. So if you have any questions, please ask. Or maybe you would like to share something with your colleagues, like your experience with boosting or something.